Good afternoon, everyone. Thanks for attending. This will be a good 30-minute nap for those of you who have no interest in geology, but thanks for staying awake if you do. So let's get started. All right, so September 28th, 2015, NASA announced that they did indeed find water on Mars. Sorry for the, I know. There are going to be more memes in here, but I thought I'd keep it nice. But in reality, it looks more like this, recurrent slope linea, these darker streaks here in the wall of Newton crater. Newton crater is named after Sir Isaac Newton, our Dark Lord and Master, and it's near the equator of Mars. So we found evidence of water, so how do we find more? If you have water flowing on the surface, you therefore have more water subsurface. Now, I'm making some assumptions here. I mean, we can get into science later in the hallway. I don't want to take up 50 minutes, I can't. But this water is contained within aquifers. Now, it's debatable whether those aquifers are frozen or liquid, but there you go. Once we get on there and do electrical resistivity, we'll figure that out. So the water is contained within aquifers, the volume of which is currently unknown. There was a talk about an hour ago. We didn't know the extent of some of these bodies of water or ice. Electrical resistivity will help us determine that. There are conduits, pathways for that water to travel from the aquifer to the surface. Some of these pathways are active, like in the wall of Newton crater. Some of them are inactive. They're old channels, and I've got some slides here in a few minutes that'll kind of nail that down a bit better. To find water, you must follow the geology. Again, I'm a karst geologist who looked at Mars photos and said, aha, I've got an idea. So, of course, it's probably the wrong way to go about it, but I did. Anyway, so I started looking at how do we find water on Earth? How do we look at the hydrology of certain areas? And so we applied it to Mars. Again, that could be a flawed way to start. But anyway, so pinpoint areas that currently have water. Again, the Newton crater, where we see water coming out of at least seeping out of the walls of the crater. So you go there. As you take a closer look, this is the Newton crater here. You take a little box here. This is zoomed in. You can clearly see old river channels. And what's kind of neat is they're old, obviously, because you have impacts above them. So they have impacted those old river systems. So it's a good place to start. So if you look at the makeup of that crater, obviously something smashed into it. So the rock in the rim of it is brecciated, and you've got tilted strata. You can see some of that strata here displaced. It's uplifted just a bit. A lot of energy has transferred from the object to the crust, and so with that, it's brecciated. But again, you get seeps of water coming from that. Now, whether this is ice up here or aquifer back in there, we'll talk about it here in a little bit. But this water is moving through in a liquid form through this brecciated and kind of complex geology based on the impact. So this is the picture that really got me going about this. This is jointing in what looks to be sandstone here, with a dividing line here, separation between some sort of shale or siltstone, and then sandstone above it. You can actually see some, I think it's right there. Yeah, you can see the dividing line where essentially water has moved through. Now, I'll also point out these cracks. These are joints. Joints in the rock are essentially relief cracks. If you take a candy bar and you break it in two, the main break of that Snickers bar is the fault, and all the little relief cracks in the chocolate coating are joints. They're fractures in rock that don't have movement along them. If they did, they would be classified as a fault. So these are joints, essentially relief cracks. But what's interesting about them, there are two different directions. You can kind of, if you use your imagination here, you can see this one kind of coming out at an angle this direction. This one is kind of going out this way. When they intersect, that intersection is about 120 degrees. That happens whether you're on the Earth or Mars. On Earth, well, it's the start for all things karst, sinkholes, caves, and so on. And I use the word epikarst here. And I know it's not true epikarst because it's not a carbonate rock. We haven't found carbonate rocks on Mars yet. But anyway, but I'm going to use the term epikarst just to kind of explain that top 50, 60 feet or so of rock. But what's neat is you have evidence of water coming down through here, eroding out this joint a bit more, and depositing in that joint probably calcium sulfate or perchlorate salts. Anyway, they've mineralized and they're harder than the surrounding rock, which is eroded away, leaving these boxwork, these veins of, again, probably calcium sulfate. But this is a good indicator that we had water flowing through these at some point in time. Maybe we could make the guess that geologically recent. Another thing here we can see, these bullseyes. If you look, these bright spots here, and as you work out, it gets a little bit darker and a little bit darker, both places. This one's obviously larger. These probably represent springs that are upwelling from the crust. Now, what's left, these bullseye deposits are probably evaporite in origin. Again, maybe calcium sulfate or perchlorate salts that are left on the surface after the water has evaporated. But another good place to look to apply electrical resistivity would be these areas. So outcrops are a great start for remote sensing, and remote sensing gets us started. It gets us so far. But it takes boots on the ground, or at least wheels, because there's an application we could use rovers to deploy electrical resistivity. But a number of geophysical techniques could be used. I'm making the argument for electrical resistivity because, well, I like electrical resistivity. I like it a lot, but it's also, it gives you the most bang for the buck, if you will. So we'll just kind of go through a basic brief list here. GPR, easy to use, but unless you're looking for a well-stratified Bronze Age archaeological site in England, it's not going to work that well on Mars for a number of reasons. If you want to know those reasons, you can catch me out in the hallway. We'll keep it short and simple here. Shallow seismic does an amazing job, and a colleague of mine will talk more about that tomorrow at 4 o'clock using shallow seismic. But it does an amazing job for the big picture. Of course, the oil industry uses this to find structures that hold oil. So you can see where you could find structures that may hold water in the future. So I won't rule it out, but the detail stuff, the small picture stuff, if you're finding small structures, voids, things like that, we'll talk about those more in a second. Using gravity, a graviometer would work, but getting it out there it's a very finely calibrated instrument. You'd have huge problems getting this thing out there, not breaking it. And then, of course, trying to maintain this thing in that environment would be difficult. But electrical resistivity, the best fit for finding, well, everything. We'll talk more about that here in a second. So the electrical resistivity 101, I'm not going to read the whole thing. You guys can read through it. But essentially, you're measuring the resistance of certain materials. You're measuring how resistant is wet clay versus dry clay, and solid bedrock versus fractured bedrock. The whole idea is that you've got enough moisture or ice to conduct that electricity. And all of this, I got to add, runs on 12 volts. So it's not an issue operating this on the surface. Here's a basic kind of diagram of what you're doing. You're putting electrical current into the ground, and as it goes from one probe to the next, it's measuring that the ohms of that material, and essentially the length of your survey. It's the rule of 1/4. So if you have a 100-foot long line, you can only go 25 feet. So the longer your line, the deeper you get to go. the wider apart your probes are, the less detail you get, but you know, you hit the sacrifice there. There's a midpoint that you're looking for, and you'll find it over time. Here's one of our setups here. I studied this for about 5 years so far, electrical resistivity and application in a karst environment, and ran it through all sorts of different scenarios. This is as close as I could get to Mars, which is the basement diggings for a mansion in the Ozarks of Missouri. But it's a dry environment, rocky, obviously, very dry. We actually had to pour a little salt water along here to get things cooking. Everything is run along this line. You can kind of make out these little blue nodes here. These are stainless steel probes that are stuck in the ground with these little cables that are looped onto it. The cables are then looped out so you don't loop on top of each other and get errors. Everything goes back to this unit here. This is the brain behind everything. That downloads to or goes through a switch box to the brain box, then your computer. You download software, it takes care of it, and gives you a beautiful picture of what's subsurface. So the quick and dirty look at resistivity data, it's as simple as you can possibly get in a way. So if we, and I'll show you guys some scans here in a few minutes, but if you look at the numbers on a scan, 0 to 105 ohms, basically a dirty ice, wet clay, water. There'd be ways to kind of filter that out too. You could kind of get an idea of the stratification of ice and the wet clays and so on. You'll see that here in a few minutes. 105 to 405 ohms, moisture-rich, weathered, and highly fractured bedrock. Imagine a moist, jointed, fractured bedrock, that one picture I showed you. Imagine a little bit of moisture in that, and that's what would come back in this zone here. 405 ohms or higher, low moisture or solid bedrock. I'll show you in some slides how noticeable that is. Also, ohm values that are, as we call, off the charts, thousands of ohms. I've had them 4,000 or 5,000. I've had them up to 100,000. These are voids in the rock, and that's what electrical resistivity does amazingly well, or find voids in rock. I'll talk more about that in a second. So this is basic data collected during each scan. Let's ignore this stuff here. This is just the program doing the program stuff, but the finished product is down here. So of course this is Earth, not Mars. There's no soil, but we've got a well-drained soil here, which is the greens on the very top. Wet clay, pockets up, these little perched water tables, kind of through the clay, the regolith, and all this stuff here is from the Ozarks. That weather is in place, so it's a deeply weathered bedrock surface. Of course, now you've got the bedrock clay or regolith interface right here, and the rest of this is weathered rock. It's still wet, and then you get into these dark red patches, which are well within that dry bedrock, solid bedrock. Okay, I lumped geologic structures and depth of bedrock into the two because, well, this slide here does a great job doing both. We're all here today basically because we don't plan on Neil Armstronging Mars. We don't want to just jump out of the spaceship, put our boot print, jump back in time to make the parade 6 months later, and we're all heroes. We want to colonize Mars at some point. So if you're building structures, you're going to, of course, want to do a geologic study before you go and you build something major on it. So depth of bedrock is important because it gives you that shot to what is solid bedrock, which is roughly down and through here. But it also does a great job with structures. And we talked about joints earlier. This is in a karst environment, but these straight lines here and here, and this one as well, these are joints. The closer you get to a fault, the closer the joints are, but you can tell these are 10 feet apart or so, 8 feet apart. But also you can see bedding planes. This here is a bedding plane through the strata, so you can see that how these two connect up. So it does a great job with geologic structures like joints and the depth of bedrock. Also in aquifer mapping, that's kind of my main argument here, is that we've got water on Mars. Let's try to figure out where it's coming from, what kind of condition is it in, and is there more? So I've added this slide here. This is one of our old ones. We've got bedrock, old Paleo Channels here, which the next slide will kind of explain this a little bit to some degree. But below this, we've got dry rock, dry bedrock that's weathered, and it starts to get increasingly more moist until you get basically your aquifer. And this is essentially how it would look in your scan. Now, there are 3D programs. You can stack the data and then do a 3D model. You can see the entire aquifer or whatever your object you're searching for in 3D. We just didn't have it, so. But as I mentioned, Paleo Channels, now this is a Newton crater. You can see this is an old flow here, an old Paleo Channel. And in fact, you can see here these sediment throws where it's throwing up material up onto this floodplain, maybe an old oxbow up through there. So running a line of resistivity around here would be ideal. You might have the same scenario as the last one here, the buried Paleo Channel here. But an important piece to this is void detection, something that shallow seismic won't do. GPR does a pretty horrible job when it does work of doing, but electrical resistivity does an amazing job. Notice over here, now you've been noticing in the previous slides that, 400 or 500 is about the high, and that's in the red zone here. Well, the issue is now we've got 5,000, nearly 5,000. This is a test site we did where we could actually enter the cave to kind of ground check or proof our work. We had a void here, a larger void that was enterable here. Well, actually, both of these are enterable. And then one that's clay filled over here. These were all long joints. The joints kind of running in this direction here, I think at 53 degrees. And you can see the depth is somewhere around 45 feet or so, like that. But anyway, the bedrock surface runs right roughly around here, like this. This is an aquifer. This is, and this is where the guy's well is at, actually. You can see the aquifer. That's wet rock, highly wet. But anyway, this gives you an idea of voids, where the voids are. You can move the probes in a little closer. You could really detail this. These were a little far apart, and so we just kind of ran over it and got the big picture. But you get the idea, void detection. So, conclusion. The deployment of electrical resistivity components on Mars can be done by remotely operated rovers at first, and later by astronauts. Nothing beats boots on the ground looking for the fine details in geology. The components are relatively lightweight today. I mean, everything sets up in about 100 pounds. One person can kind of lift it around. But through some moderate research and development, you could shrink it and lighten the load substantially. And make it easier to deploy, cheaper to launch, and so on and so on. The volumes of data recovered from resistivity would have numerous uses. I was sitting here and listening to some of the talks, and you're talking about asteroids and things like this. You could run this on that and figure out what kind of components you have in there, different metals and the geology. This is easy to set up. But that's part of the volumes of data. You could get not only the aquifer mapping and depth to bedrock and so on, static water levels. The static water levels are important. It'll be talked more tomorrow, my colleague, as she talks about that a little more in detail. But anyway, a lot of uses with the data. Again, void detection. But also, the cool part about void detection is the search for life. When you get deeper, I mean, the surface of Mars it's a sterile environment between perchlorates and, cosmic radiation. Everything on the surface is pretty much screwed in a way. But The search for life, if it's in a hole, if it's in a void, in a cave 50, 60, 70 feet down, it escapes the vast majority of cosmic radiation, potentially. And if it's wet, then even if it's perchlorate-rich water, which it probably is, some organisms can metabolize perchlorate-rich water, but that's going to be the hot spot for the search for life. You find a cave, you have a potential for life. But also it's a potential safe place for humans to escape the cosmic bad guy out there. If a solar flare like the one that's hitting the Earth tonight, I believe, obviously Mars doesn't have the capability of protecting you from that, but a cave might if it's deep enough. So, any questions? Yes?
So, we're working on a lunar ice mining concept that involves a rover, a large area rover that goes around and gets what? Say how. What we'd really like to be able to do, so the lunar permafrost is unknown. But we can reach down a meter or two to get it using our technology. What we'd really like to do is be able to rove to a spot, stop, and see what the density of water and the profile of the permafrost below us is. In some cases, the first 10 centimeters are regolith, dry regolith, and then the water concentration might be 5 to 10% by mass, down to a depth of a meter or two. We'd like to get a feeling for that before we stop, and we'd like to get a feeling for what the permafrost looks like in the crater around us. How would you apply this technology to that problem?
You could have a rover that is designed to essentially put, now, we use 28 probes, but, we're doing this for research. We're doing this to look for geologic structures. We're looking for, really high resolution. You could use 4, to really simplify it. That rover could plant 4 stakes into the ground. They could be, a couple of feet. It gets you down in there enough to get moisture. It'll run on ice. I've used it in ice. Once you apply those probes and hook up the cables.
Can it tell you what's between the 4 probes, basically?
Yes, in a straight line.
Now, how far away can we put the probes in order to have it make us a map of the permafrost?
So you can run, it depends on your unit. Now you could run like an 8-channel unit, and you could have 8 lines run at one time. Everything goes back to one switch box, an 8-channel switch box, and into your brain box.
What you do is you pulse the probes at different voltages and look at different combinations.
So essentially, let me run back to this slide here. You're gonna put, it goes from the number 1 probe to 2, and then 1 to 3, and 1 to 4, and 1 to 5.
All the different permutations.
Exactly. It runs at 256 different runs. And as we run back through this here, 12 volts. Yep. So you could run this off of solar. I mean, it's easy to do. Even a small, some sort of generation unit would.
The volts are, if I'm only putting the probes in this deep, how do I get depth data?
Here we go. Again, your length. So if you put one across the entire crater from rim to rim, it would give you an exact. So say your crater is 100 yards wide. You would get roughly 25 yards deep at that point, because it's running from each pole. It's running down deep through, and again, the longer the line, the deeper you're getting. So I'm the director of the Missouri Institute of Natural Science, but I'm also I have a geologic consulting business as well. What's that? Oh yes. Well, you'd think I would have come prepared, but those are still in Springfield, Missouri. But I'll get you my information. So I apologize for that. I remembered everything, including my sunglasses and everything else. And my wife was watching, going, "I told you forgot your business cards." But anyway, yes.
How long does it take to set up and lay it all out? How long does it take to actually run each flip switch?
Good question. Now there are a number of dipole. Dipole is one array. Winner, Schlumberger. There's a number of ways to do your array. Now dipole seems to be the catch-all. I mean, it works the best and it's the easiest. It's a single line of probes. It depends on how many probes you have, how long they are, how many channels you're going to run is just a single line. You're talking 8 channels. So that the setup time will vary based on your array. But a person that really knows what they're doing, of course, you'd have the limitation of if you're doing it as a person as a spacesuit and all that stuff, but a couple of hours,
Like doing all that sort of S hooking.
Yes, that's it, yeah.
Is there a way to put that on the grid where you just lay it down like
Oh, yeah, sure. I mean, yeah, with a little R&D, you could make this a lot easier than we're doing it now. And then to run it, honestly, about 48 minutes of run time, and you have data like you saw on the slides. So, yeah.
How big of an area can you do at a time?
That is limited to your cable length. So, now your cable, it runs right along there, so you're only seeing a slice. You're seeing a couple-inch wide slice through the ground. So if you want to have a mile long, you better have a mile long cable to do that. So.
How would the information vary between this and, say, ground penetrating radar?
GPR, based on moisture content, can give you some false echoes. If you don't have something to transmit that signal deeper, then you have issues. You can have perched aquifers. You can have little wet lenses that bounce it back at you. There are issues, especially in a dry environment of Mars. The more rocky you get, the less moisture you get, the rockier you get, and the more moisture you get, the more problems you get. Where electrical resistivity, that's not a problem. The only drawback to electrical resistivity is here on Earth, because you get chain link fences and rebar and concrete and then buried, utilities, things like that. So that's where you get the limitations are here, but until we have big colonies on Mars, you wouldn't have those limitations at first. So.
What about thumpers?
It takes a lot of energy. Yeah, if you're doing shallow seismic, you would have to have an energy source to thump the ground. Now, you could do it with a sledgehammer and a trigger device on it, and that'd be fine. But to really get deep, you're going to need a thumper or set off an explosive charge. All possible. That's why I didn't rule it out. But shallow seismic would be really a close second, a very close second to electrical resistivity. Mm-hmm.
So which one of these would be the best technology?
Electrical resistivity, hands down, to find voids. Shallow seismic doesn't find voids. So it is horrible at doing that. Even the best operator, I used shallow seismic for 5 years, and I still can't find a void. You can find little blips that might be, but it could be, a buried utility. It could be a tree root, all sorts of things that can kind of fool you a little bit. So yeah, I know what I'm doing with both forms, and horrible at shallow seismic with finding voids. All right. Thanks, guys.